Okay, we're going to pick up in chapter 8 with torque. So Newton's first law has the same form for rotational motion as well as translational motion. If you remember, the first law said that in the absence of a net external interaction, the natural motion is one in which the rotational velocity remains constant. So basically, if it's not rotating, it's going to continue to not rotate. If it is rotating, it's going to continue to rotate with that same rotational velocity. So in this next slide, what you're seeing is you're throwing a wrench. Okay. And on the slide, it tells you, well, if you imagine riding along with the wrench, you can see that the wrench rotates about, notice the white dots. And it rotates by the same amount between those successive flashes. So that tells you that that rotational speed is constant. Now, a change in your rotational speed can only occur when there's a net external interaction on the object. So that interaction is going to involve forces. But unlike what we talked about with translational motion, now the location at which the forces act is as important as their sizes and their direction. So what we're saying is the same force can produce different effects depending on where and which direction it's applied. So a good experiment with this would be a door, okay? If I were to go to the door and I push directly toward the hinges, or I pull right by the hinges, the door's not going to rotate. The only way that rotation is going to occur is when that horizontal force is applied in any other direction. Your largest force is going to be when that force is perpendicular to the face of the door. Okay? So even though I'm going up to a door and I'm going to apply a force perpendicular to that door, it's going to depend upon where I'm pushing. Okay? If I'm pushing close to the hinges, nothing really happens. If I'm pushing away from the hinges, then I'm going to see motion. So if you've ever wondered why do we put a doorknob where we put it, it's because of the torque. So torque is represented by this Greek symbol. It's known as tau. And your torque is measuring the effectiveness of a force causing an object to rotate about a pivot point. Notice this picture of the wrench. You see our pivot point right here. Then when we look at this diagram, we see we have a radial line that goes and starts at the pivot point and goes through the point of application of the force. R is showing you the distance from the pivot point to the point of application. V, which is this symbol right here, is going to be the angle measured from the radial line to the direction of the force. Now, torque has the units of a Newton times a meter. What we're going to do is we're going to restrict ourselves to the case where the force is perpendicular to the radius. So that's going to allow us to say that the torque equals R times F. And this, my symbol didn't come up. This should be top. So torque equals R times F. So in case you haven't gathered, basically torque is just the rotational equivalent of force. So torque is a vector, lies along that axis of rotation, and it's easier for us to describe a torque by the effect it has in rotating an object that's initially stationary. So if we look at these two little pictures, we can say if your object rotates clockwise, we say that the torque is clockwise, and we say that it's a negative torque for our clockwise rotation. If our object rotates counterclockwise, we can say the torque is counterclockwise, and it's considered to have a positive torque. So basically, when we have developed this concept of torque, it let us restate Newton's first law in terms of rotation. So the rotational velocity of a rigid object remains constant unless acted on by an unbalanced torque. And remember, for a vector to remain constant, both the magnitude as well as its direction must remain constant. Now, we just said that torque was equal to a product. So you can see why the same applied force can produce different torques on an object. If the torque is increased if the force is applied farther from the axis of rotation. So if I'm trying to loosen a nut that I can't get off, the biggest torque is going to occur when I either push or pull on that wrench farthest from the spot that's around the nut. So a lot of times you'll see people put a pipe on the edge of the handle to the wrench, and thereby they're increasing that distance, so they're increasing the torque. So it's easier to loosen that nut. Okay, let's try our problem. So in this one, they want you to imagine that you have a flat tire and one of the lug nuts is stuck tight. Your wrench is 3 meters long. So R is going to be 3 meters. Let's redo that. Okay, R is actually 0.3 meters. And you weigh 500 newtons. So the force that you're exerting is your weight, which is 500 newtons. So what's the maximum torque? Well, torque equals R times F. So the torque is going to equal 0.3 meters times 500 newtons. So your torque will equal 150 Newton meters. Now, if we look at this question, suppose that this is not enough, but you found a pipe in your car that could be slipped over the wrench, tripling its length. What torque could you now apply? Well, remember that torque equals R times F. So now if I'm going to triple R, my torque is going to be 3 times as large as it initially was. So initially, my torque was 150 Newton meters. And now I've tripled it. So now my new torque is going to be 450 Newton meters because of putting that pipe over it. Now, there might be a case where there's more than one applied force. Okay, so in this case, your net force is 0, but the net torque is not 0. So I can have a pair of forces that are not going to produce any translational acceleration, but they can still produce a rotational acceleration. Notice in the picture, you have two forces. They are equal in size. The length of that blue arrow is the same, but they're acting in opposite directions. So they're going to cancel each other out in terms of force, but my stick is going to accelerate clockwise because of the torque about that center of the board. Okay, so situation where net force is 0, but I'm still having that rotational effect, so that torque. If you've ever played on a seesaw, okay, so the physics behind the seesaw, you take the weight of each person and you multiply it by her distance from that pivot point. So here's my pivot point right here. Okay, and that's going to give you the torque that she applies to that board. If the two torques are equal in magnitude, opposite in direction, there's not going to be any acceleration in a rotational sense. And then it wouldn't be any fun playing on a seesaw. Okay, because what? You're alternating between rotation. First it's go up, then the other one goes down, and so forth. So two people with different weights can still balance the seesaw. It all depends upon where they're exhibiting, where they're located from that pivot point. And depending on where they're located, your torques could be equalized. So let's do another problem. So in this one, we want to know the torque on a bolt. So we're going to find out what the torque's going to be. If you're pulling with a force of 200 newtons, directed perpendicular to the wrench, of length 20 centimeters. Well, we know that torque equals R times F, and I know my units of torque are a Newton meter, so that tells me I need to convert centimeters to meters. So 20 centimeters is going to be 0.2 meters. So then my torque is going to be 0.2 meters times 200 newtons, and that's going to give me a torque of 40 Newton meters. There's another one. You're asked to find the torque that's produced by opening a jar of pickles. If the lid has a radius of 3.8 centimeters and the force that's exerted perpendicular to the lid is 150 newtons. So again, we have centimeters. We need to convert to meters. So that's going to be 0.038 meters. So my torque is R times F, which is going to be 0.038 meters times 150 newtons. And that's going to give me a torque of 5.7 Newton meters. So we also have a quantity that's called or known as the rotational inertia. And your rotational inertia depends upon the amount of mass and the distribution of that mass. Okay. as you can see in this merry-go-round. Notice the first picture, the mass is concentrated around the rim, so it's a lot harder to get that merry-go-round to spin, whereas the picture on the right, the mass is concentrated in the center, so it's easier to get it to start spinning. So farther away your mass is located from the point of rotation, the larger your rotational inertia. Your net torque on an object is equal to rotational inertia times rotational acceleration. So in Newton's second law, for rotational motion, it's going to be analogous to that for translational motion. If you remember, we had the net force is mass times the acceleration. Now for rotation, what we're doing is replacing torque for force, and we're replacing the mass with rotational inertia, also known as moment of inertia, and we use a capital I for it. So our new form of Newton's second law is the net torque equals the rotational inertia times the rotational acceleration. So we have net torque equals I alpha. And right here is a mistake. This should say alpha. There's a mistake with my symbols. So just like we saw when we were dealing with translational acceleration, that it always points in the same direction as the net force that's causing it, well, we see that our rotational acceleration must point in the same direction as the net torque. So the net torque is going to lie along that axis of rotation. So you ever go to a circus and you see people going on the high wire? Okay, well, when they're holding that pole, they're actually increasing their rotational inertia by carrying that pole. So that's what's allowing them to balance. If you've ever walked on railroad tracks, if you had your arms tight against your sides, you couldn't walk on it. So what do? We take our arms, like in this picture, and we spread them out, and therefore we can balance on the railroad tracks and walk. Now, with rotational inertia, we have our common shapes. They have moments of inertia, okay? And this diagram gives you, or this table gives you some common shapes and their moment of inertia. You do not have to memorize this table. If I give you problems like this on an exam, I would give you the moment of inertia, or I would give you a table where you would look up the moment of inertia. So let's do some problems where we're going to be needing moments of inertia. Okay, this first problem, we have a 8-kilogram wheel. So we know our mass is going to be 8 kilograms. It has a radius of gyration of 25 centimeters. And you're asked to find the moment of inertia. Okay. You're also asked to find the torque that's required to give it an angular acceleration of 3 radians per second squared. Okay. Well, we have a wheel. So we go back and we look at our figure and we see to find our moment of inertia for a wheel, our formula is going to be I equals mr squared. So therefore, our moment of inertia is going to be 8 kilograms times r squared. But now we see r is just in centimeters, so we know we have to convert it to meters. So that's 0.25 meters. So we're going to multiply that by 0.25 meters, and that's going to be squared. So therefore, our moment of inertia is going to be 0.5 kilograms meters squared. And now we're asked to calculate the torque. So the torque is going to be I times alpha. Well, we just calculated I, 0.5 kilograms meters squared. And our alpha is 3 radians per second squared. So torque is going to be 1.5 newtons times meters. Okay. You don't include the radians as part of your units, just like you wouldn't include revolution as part of your units. Okay, we're going to end this section of recording, and we will pick up with the slide on center of mass in our next recording section.